For centuries, humanity has looked to the night sky, searching for answers. Among the greatest mysteries are black holes, objects so strange, so powerful, that even light cannot escape. But how did we come to believe in them? The journey begins not with Einstein, not with Hawking, but with Isaac Newton. From Newton's laws of gravity to Hawking's radiation, the story of black holes is the story of human curiosity. Tonight, we will trace that story, from the first whispers of dark stars to the modern revelation that even black holes may one day die. Isaac Newton, 17th century. His masterpiece, the Principia Mathematica, revealed the law of universal gravitation. According to Newton, every mass in the universe attracts every other mass with a force proportional to its weight and inversely proportional to distance. With this law, the cosmos could be predicted. The motion of planets, the fall of an apple, all explained with mathematics. And yet Newton's gravity carried a hidden possibility. What if a star became so massive, so dense that its escape velocity, the speed required to break free from its gravity, exceeded the speed of light? If light could not escape, then such a star would be invisible, a dark star. John Michel, in 1783, and Pierre-Simon Laplace later expanded this idea using Newton's equations. They imagined objects so heavy that nothing, not even light, could break free. It was the first description of what we now call a black hole. But to Newton, and even to Michel, this was just speculation. No evidence, no mechanism to explain how such a star could form. The idea drifted into obscurity, until Einstein changed everything. In 1915, Albert Einstein unveiled the general theory of relativity. Gravity, he said, was not a force pulling objects together, as Newton thought. It was the bending of space and time itself. Mass tells space how to curve, space tells matter how to move. Within Einstein's equations lay a shocking possibility. Carl Schwarzschild, solving Einstein's field equations, found that if enough mass were compressed into a small enough region, space-time would curve infinitely. This was the true birth of the black hole. Unlike Newton's dark stars, Einstein's black holes were not hypothetical curiosities. They were inevitable. If a star collapsed beyond a certain point, no force in the universe could stop it. For decades, physicists debated whether these objects were real. Some thought the equations were too extreme, just mathematical artifacts. But slowly, evidence began to mount. Stars orbiting invisible companions. Light bent in ways that could not be explained otherwise. Black holes were no longer fantasy. They were real. Enter Stephen Hawking. A young physicist in the 1970s, confined to a wheelchair but with a mind sharper than any. Hawking asked a daring question. If black holes trap everything, even light, what happens when you add quantum mechanics to the picture? His answer shocked the world. In 1974, Hawking showed that black holes are not completely black. Through quantum effects near the event horizon, black holes can emit particles. Tiny amounts of energy leak out. This became known as Hawking radiation. The implication was staggering. Black holes are not eternal prisons. They are not immortal. Given enough time, they will evaporate. A black hole the size of a star might last trillions of years, but eventually, it would vanish into nothing. This revelation created the black hole information paradox. If black holes disappear, what happens to the information about what fell into them? Quantum theory says information cannot be destroyed, but general relativity says it can, which is true. Decades later, the paradox remains unsolved, one of the deepest mysteries of modern physics. Newton imagined gravity as an invisible force pulling objects together. His universe was mechanical, predictable, timeless. In his framework, a dark star would be permanent, eternal, light trapped forever. Hawking's universe is different. Gravity is the warping of space-time. Quantum mechanics rules the smallest scales. In his framework, black holes are not eternal. They glow, they shrink, they die. Newton gave us the seed, the possibility of objects so massive that even light could not escape. Hawking gave us the twist. Those objects are not forever. They are dynamic, fragile, and filled with paradoxes that challenge our understanding of reality. From Newton's dark stars to Einstein's curved space-time, from Schwarzschild's equations to Hawking's radiation. The story of black holes is a story of science itself. Each generation peered deeper into the darkness. Each discovery revealed more questions than answers. Newton showed us that gravity rules the cosmos. Hawking showed us that even the mightiest objects in the universe are not immune to time. And so we stand, still searching, still questioning. black holes remain the most mysterious objects in the universe, not only swallowing matter and light, but swallowing our certainty. Perhaps, in the end, black holes are not just cosmic monsters. They are teachers, forcing us to confront the limits of knowledge and reminding us that in the heart of darkness, the greatest mysteries still await.